So welcome to this next lecture on plant-wide control basics. Today we are going to look at welcome to this next lecture on plant-wide control basics. Today we are going to look at liquid level control in recycle loops. We are going to begin with liquid level control in a single tank. Then we're going to look at liquid level control in n tanks in series, and then finally we're going to look at liquid level control of n tanks in series with a recycle. And the main idea behind doing this is to figure out does recycle dictate that the control system be structured in a particular way so that you get dynamic advantages or you avoid dynamic pitfalls. That's the basic idea that we're going to pursue. So let's get on with it. So consider the simplest of problems, single tank, single flow in, single flow out. There is a flow in which is independently set and the tank level is being maintained by adjusting the flow out. A level controller does that. Level controller manipulates Q out to hold V, and for this system let's just write the material balances. So the material balances are of the form we have dV by dt is equal to Q in minus Q out, Q in minus Q out. And Q out, because it's a PI controller, may be written as Q out is equal to Kc times, and if the volume increases, Q out should increase, so there will be no negative sign there, so we will have Kc times V plus 1 by tau I times integral of V dt, and it's all deviation variable, so there will be no bias term. And now if we plug this into the above equation and take Laplace transform of both the sides, what we will get is S of V is equal to Q in minus Kc times tau I S plus 1 divided by tau I S into V, multiplying both sides. Then what we get is tau I by Kc times S square plus tau I S plus 1 times V is equal to Q in times tau I S divided by Kc. So what we get basically is that V divided by Q in is equal to tau I by Kc times S divided by tau I by Kc times S square plus tau I S plus 1. And if you want the variation in Q out with respect to Q in, then all you do is you multiply this by see from here what we have is Q out by V is equal to Kc times tau I S plus 1 divided by tau I S. So if you multiply these two transfer functions, this and this, what you get is Q out by V. Oh, no, not Q out by V, man. Q out by Q in is equal to Kc by tau is cancels out, so what you have is tau is plus 1 divided by tau I by Kc times S square plus tau I S plus 1. So these are the two transfer functions, and if you want to look at the root locus, in order to look at the root locus, we see that G process from here, you get G process is the relationship between the effect on the output V by Q out. That's G process. V by Q out. V is the controlled variable, Q out is the manipulated variable. That's equal to minus 1 by S. So that's equal to GP, and GC is in front of you, and Kc would have a negative sign and so on and so forth. Forget about all that. So basically what you get is G open loop is going to be equal to, after accounting properly for signs, it's going to be Kc times tau is plus 1 divided by tau I S square. So this has got two poles and one 0. The poles are at s equal to 0, and the 0 is at s equal to minus 1 by tau I guess. Yeah, so one can draw the root locus, and the root locus would turn out to be, let me draw it. Let's see. There's two poles here, and there's 1 0 here. There's between the poles and the zeros, there's not going to be any locus, because the number of critical points to the right is even, because there are two poles at the origin. Will locus exist here? Yes, because there are 3 points to the right, 3 critical points, which is an odd number. The overall order of the system is numerator order is 1, denominator order is 2, so 2 minus 1, the overall order is 1. So because the overall order is 1, you will get one asymptote, and that asymptote is already drawn there. It will have an angle of minus 180 degrees, and so what you have is there will be two branches starting from the two poles at the origin. One of them will end up at the 0, and the other one will end up in the asymptote. So the root locus would look something like this, and its mirror image. So that's the root locus. Yeah. So that would be the root locus. The other simplification, or the way I have usually like to look at things, is to consider let's create some space by erasing some of the stuff out. Okay, so we will have to go to the eraser. The other thing that I wanted you to note is that many a times it is useful to say that, not useful, that's the way I like to look at things, just to say that tau I is equal to a times tau, where tau is the residence time, so tau is equal to steady state hold up divided by steady state flow through the tank. So that's sort of the okay. Yeah. It can also be shown that Kc can be put as some factor f divided by tau. Okay, and you can see from here Kc has Q out is meter cube per second, V is meter cube, so Kc has units of 1 by second, so it's time inverse. And so this sort of makes sense. To get further clarity, you see, let's look at a proportional only controller. Kc would be by definition would be the change in Q out that you make basically at steady state, initial versus final. So initially you are at steady state, finally you are at a new steady state, the change in the flow divided by the change in the volume. And if the volume changes by 1%, we are saying change the outflow by 2%. Okay, so for example, if the holdup changes by 50% of the base case value, so V final minus V, so delta V is equal to 0.5 of steady state holdup, let us say, then Q out should double. So delta Q out doubling means this equal to, it was initially at Q bar, then it went from Q bar to 2 Q bar, so the change is Q bar, and therefore Kc will be, in this example, Q bar by 0.5 V, which is 2 times Q bar by V bar, which is 2 by tau, which has the form F by tau. And this F is the sort of the how tightly you're tuning. Right now we used a factor of 2, you could use a factor of 4, more aggressively tuned, or a factor of 1.5 maybe, or 1 less aggressively tuned. So this is used quite often, and if you use this, then what you will get is V by Q in is equal to A tau I square by F into S divided by A tau I square by F into S square plus A, not tau I, man, this is tau, sorry, we want to put everything in terms of tau. So this is, yeah, A tau S plus 1, and we also have Q out by Q in is equal to A tau S plus 1 divided by A tau square by F times S square plus A tau S plus 1. So we have derived these transfer functions, and now it's time to proceed further. So that's what we have. We've got the original differential equation, rate of change of volume is equal to Q in minus Q out. We've got Q out as a PI controller, and this gives this as this, and G open loop will be this. Actually this should actually be plus. This should be plus, because the controller gain will have to be negative if you use error in the classic definition of set point minus process variable. The way it is written here, it is in the classic definition of process variable minus set point. So once G open loop is that, you get a root locus of the kind that I just talked about, and we continue, and if you do the math, this is what we get. And this is what I said, you use tau as the residence time of the tank and tau I as A times tau and Kc as F by tau. Then this is what you get, this is what we have derived. And if you look at the root locus of the system and we consider, for example, A is equal to 2, that means your integral time is twice the residence time, which seems reasonable. Then if you use an F equal to 2, that is critically damped, and you can substitute it here. So suppose you put A is equal to 2, F is equal to 2, you get tau square S square plus 2 tau S plus 1, which is tau S plus 1 whole square. So that's a critically damped system with 2 repeated roots at S is equal to minus 1 by tau. So for A equal to 2, F equal to 2, the system is critically damped. If you look at the root locus, that's the way it looks like. And tuning a PI controller for liquid level systems can be counterintuitive. It can be counterintuitive in this sense. Let's say you're using a Kc for which you got, that's the point where you are, and if you increase the Kc, you go further down. So the real part of the root has increased in terms of magnitude and the imaginary part has decreased. That means as Kc is increased, the damping or the under damping actually decreases. Usually what happens is, you increase Kc, the system becomes more under damped. So here is a region. On the other hand, if you're using too low a Kc, which is usually not the case because you cannot use too low a Kc, but just for the sake of argument, if you're using a Kc over here, so let's say this point, and then you go further, increase the Kc, then you'll go here. Now you can see that, okay, as Kc is increasing in that region, the under damping is also increasing. So at this point here, you are critically damped, and if you increase the Kc, then you start getting two real roots that are distinct, one here, one here. Yeah. So that's the kind of system that we are looking at. The tuning can be complicated, and so what I did was I changed the tuning parameters, and ran a few simulations and saw what kind of responses we get. So let's look at those responses. There we go. So you can see that if you have a P only controller, you get those red dotted curves. So the Q out varies as a smooth exponential. If Q in is varied by 1%, Q out rises exponentially to 1%. That's Control-Shift-3. So you see, there we go. That's a nice smooth rise to 1%. The volume, which would continually increase with no control because there's an integrator in there, it doesn't continually increase because of the proportional action. It settles and there is an offset, and because the gain is 2, the offset is half of that, 0.5%. Yeah, because we're using A equal to 2, F is equal to 2. So that's not A equal to 2, A is equal to infinity for P control, F is equal to 2. Okay, so that's the offset that you get with P control. If you use a PI control, you see, no matter what kind of curve it is, the blue, the magenta or the black, what you find is, see, at time t equal to 0 I gave a step, at time t equal to 0 there is a step, goes to 1, Q in, and stays at 1. Perfect level control. So let's say we are looking at the black curve. Okay, so if you're looking at the black curve, then this area represents the volume that has accumulated in the tank. Because of integral action, you want the tank level to go back to 0. This extra volume that has accumulated in the tank must be discharged, so flow out must become more than flow in, and so you got this area. And the two areas are equal, and that is why the level gets driven to 0, no offset. Okay. But another point to be noted, look at the P controller response. The response completes in about what, 2 time constants. Here the response is taking anywhere from 4 to 5. Maybe this is what it takes. So with PI control you take longer to settle down. With P control you settle quicker, because you're not trying to drive the level back to its set point. Okay. So from these simple arguments, what we see is that PI control necessarily causes a bump in Q out in order to drive the level back to set point, and of course there is no offset in the hold up with PI control. However, the response is noticeably slower. P control on the other hand gives smooth Q out variation. There is offset in the hold up with P control, and the response is noticeably faster compared to PI control. So these are some of the things that we have for a single level controller. Main thing, PI control will give a bump in flow, P control gives no bump but offset. Okay. Continuing. Now let's look at n tanks in series. If you're looking at n tanks in series, then what we have is Q naught over there, and Qn is the flow out from the final tank. If we've got n tanks in series, then you have Qi divided by Qi minus 1. This is going to be A tau s plus 1 divided by A tau square by f times s square plus A tau s plus 1. So Qn by Q naught is going to be Q1 by Q naught times Q2 by Q1 and so on and so forth times Qn by Qn minus 1, and that essentially turns out that what we get from this is that Qn by Q naught is actually equal to A tau s plus 1 divided by A tau square by f times s square plus A tau s plus 1, the whole thing to the power n. That's quite straightforward. Don't need this. Now if you want a transfer function for Vn, so if you want a transfer function for change in volume of the last tank divided by Q naught, that will be Qn minus 1 divided by Q naught times what are we doing? Times Vn by Qn minus 1, and this will cancel out. Vn by Qn minus 1 we saw in the previous in the previous slide. If you look at it, yeah, there it is. See here, there it is. V by Q in, that's what this is. So we're going to use this. We're going to use this here, and so what you get after doing the necessary math, this is going to be equal to A tau S plus 1 divided by A tau square by F S square plus A tau S plus 1 to the power n minus 1 times A tau square by F times S divided by what? Divided by this guy, A tau square S square by F plus A tau S plus 1. So what you get essentially is Vn over Q naught is equal to A tau S plus 1 to the power n minus 1 times A tau square divided by F times S divided by A tau square by F times S square plus A tau S plus 1 whole to the power n. So you got this expression right here and this expression right here as your transfer functions for n tanks in series, and we'll just quickly recap the same over here. Yeah, so this is a reiteration of what we already have, and so from this is what we get. And if you look at the characteristic equation of this system is this chap right here, this guy, the denominator equal to 0. So that's your characteristic equation, and the roots are basically solve the quadratic, it's in front of you. So what you get essentially is, see if f is the, or a, one of the two, if a goes too small, that means you are using very aggressive integral action, then the negative term inside the square root will become very large and you will start getting imaginary part, complex conjugate, but the real part will always remain negative. So you will always get a stable response. The response may be overdamped, critically damped, or underdamped depending on whether AF is greater than 4 for overdamped, AF is equal to 4 for critically damped, and underdamped will be AF is less than 4. Yeah, because if AF is less than 4, the negative term is greater than 1. If negative term is greater than 1, the term under the radical is negative and you get plus minus I square root, whatever. Yeah. So critical damping means you can have oscillations. Yeah. Oh, sorry. Underdamping means you can have oscillations. Or Control Shift Delete. Okay. So we continue. What I did was simulated the system for n equal to 1 tank, n equal to 4 tanks, n equal to 8 tanks, and n equal to 12 tanks, and all the level controllers are Pi or P only. For a Pi controller, A equal to 2, F equal to 2. For a P only controller, A is infinity, F remains 2. Okay, and what you see from the response is that if you have a P only controller, those are the dashed curves. You can see that the Q out percent response, the subplot, the first subplot on the top, you can see the Q out varies very smoothly. You give a 1% change in inflow, outflow changes from 0 to 1% in a smooth exponential, delayed exponential, and the delay is 1 second. So you can see the Q out varies very smoothly. You give a 1% change in inflow, outflow changes from 0 to 1% in a smooth exponential, delayed exponential, and the delay is 1 second. So you can see the Q out varies very smoothly. You give a 1% change in inflow, outflow changes from 0 to 1% in a smooth exponential, delayed exponential, and the delay is 1 second. So you can see the Q out varies very smoothly. You give a 1% change in inflow, outflow changes from 0 to 1% in a smooth exponential, delayed exponential, and the delay is 1 second. So you can see the Q out varies very smoothly. You give a 1% change in inflow, outflow changes from 0 to 1% in a smooth exponential, delayed exponential, and the delay is 1 second. So you can see the Q out varies very smoothly. You give a 1% change in inflow, outflow changes from 0 to 1% in a smooth exponential, delayed Delay increases as the number of tanks increases. So the blue tank is corresponding to n equal to 1, magenta is n equal to 4, that's further delayed. The black is n equal to 8, that is further delayed, and the red is n equal to 12, that is further delayed. So the dashed curves are for peak control, smooth exponential rise to the final steady state. That's true for Q out, that's also true for V, the hold up. Now if you start using peak controller and all the peak controllers are identical, they use A equal to 2 and F is equal to 2, you can see the response. You start getting bumps. The bump is going to be there because of trying to drive the levels to 0, or the offset in the level to 0, and you can see that the oscillatoriness of the system increases as the number of tanks increases. In fact, you get more oscillations and more sluggishness both together. So the red curve, for example, it takes about what, t by tau. By the way, the x-axis is scaled t by tau and not t itself. You can see that the red response has not settled in. Let's compare red dashed and red solid. Solid is pi, dashed is p. So you can see that the red response is completing 95% or I don't know 96-97% in about 8 time constants, whereas the red response for the peak controller is completing in about 4 time constants. Yeah, so the peak control response is much faster, no bumps. The PI response is bumpy, more sluggish. Yeah, so that's sort of the conclusion that we get. So PI control, you get large bumps in both Q out and V, significantly longer settling times compared to P controllers. There is no steady state offset in the level, even though we have not shown it, but we understand from previous results. P control, smooth transients with no bumps, significantly shorter settling times. There is a noticeable steady state offset in level as seen in the previous result. From all of this, because the purpose behind putting these tanks is to filter out flow variance so that the downstream unit sees less significant flow variability, it's quite obvious that P control is good. So we recommend P control for smooth process operation in the sense that flow transients get filtered out. There is no amplification in flow variability. P controllers, on the other hand, amplify flow variability in the sense you start getting bumps. Okay. Now let's look at N tanks in series with recycle. So we've got over here the flow out from the nth tank. The flow out from the nth tank it is split into two. R fraction of what's coming in is recycled. A fraction R of what's coming in is recycled. A fraction 1 minus R is taken out as product or is discharged from the process. Okay. Now you got all the level controllers are as before in the tanks in series. Over here you got two options. One option is that you control the flow in, Q in. This is what is being done here. The other option is, and let me show you the other option and then we'll talk about it. The other option is that you hold the flow, total flow going to the first tank, recycle plus fresh. So this is the other option. Yeah, so instead, so in the first option in CS1, you are setting Q in, operator is setting Q in. In CS2, operator is setting Q0. The set point that he is setting is Q0, and Q0 is the flow to the first tank, total flow to the first tank, Q in plus recycle. Yeah. Okay. So there are these two options, and now the point that I wanted to make was, because here in this case you are holding this flow, so as far as the system is concerned, the dynamics will be governed by tanks in series, because what is changing is the flow going into this tank. On the other hand, so this is actually tanks in series. What's going on here, which is how conventionally most conventional control systems will be like this, and I really don't like it. What's going on here is, you make a change here. Because you make a change here, things change through this cascade. This flow increases. As this flow increases, this increases, and then this of it goes round and round in circles. So you got to account for the recycle effect. Must account for recycle effect. This is not tanks in series, but tanks in series where you must account for the recycle effect. Must account for recycle effect. Okay, so let's derive transfer function models for variation in Qn in response to a change in the throughput manipulator Qin for CS1, a variation in Qn with respect to a change in the throughput manipulator Q0 for CS2. Those are the two transfer functions that we are looking for. By the way, the recycle splitter degree of freedom is adjusted to keep R constant. Okay, there's a degree of freedom associated with the recycle, and what we are saying is the split is fixed. R is fixed. So I have not shown a valve there. If there was a valve, we will adjust that valve to keep that ratio fixed. Okay, so that's that. And of course we are assuming perfect flow control as we did for the single tank and tanks in series. So these are the two assumptions that we have. Under these assumptions, let's now derive for CS2. I mean, things are pretty simple. Oh dear. For CS2, things are pretty simple. You got n tanks in series, and therefore Qn by Q0, because Q0 is what you're manipulating, is going to be that's going to be the transfer function for CS2, Qn to Q. For CS1, on the other hand, we will have to derive. So what we have is actually in CS1 is that Q0 is equal to Qin plus Q recycle, and Q recycle is equal to R times Qn, and let me call this G. So Qn is equal to G times Q0, and Qn, oh dear, क्या है यार, ये सब लिख नहीं रहा. So Q0 is equal to Qin plus R times G times Q0. So what that gives is Q0 by Qin is equal to 1 over 1 minus Rg. Substitute this into this, and then what we get is Qn is equal to G over 1 minus Rg divided by Qn. Sorry. So Qn by Qn is this, and so what we get is Qn by Qin is equal to, if you do all the necessary math, what you'll finally get is numerator will be a tau s plus 1 to the power n the denominators of the numerator and denominator will cancel, so that will be that, and 1 minus this will be, yeah, so this will be a tau square by f times s square plus a tau s plus 1 to the power n minus a tau s plus 1 to the power n again. So that's the transfer function that we get for CS1. So this is for CS1 and this is for CS2. Okay, so that's that. So let's continue. So CS2 of course is tanks in series, so that's what we've got. Characteristic equation is as above, and you can see that if the individual tank level controller is stable, you're going to have the n tanks in series also going to be always stable. CS1, the derivation that we did, so we get the transfer functions as shown, and here the characteristic equation is this guy. Notice that in this guy we have this guy being subtracted out, and because it is being subtracted out, there is a possibility for improperly chosen values of a and f, where you can have some of the roots go into the right half plane. Okay, so this system can go unstable. So here we have an example, we have a system that can go unstable if we don't watch out. Even though a and tau seem reasonable for a single tank, when you connect them in series and you have recycle and maybe the recycle fraction r is large, you can have instability. Okay, continuing, I did some simulation to get some results. So we have P control only for CS1. You give a step change in Qin, and what we did was number of tanks is 4, f is used as 2, tau is 5 minutes. For P control, a is of course infinity. So here are the responses when using a P only controller in the first figure, and you can see the transients are exponential, but what you do notice is as the recycled fraction is increased, response takes longer to complete. So the blue curve takes about, I don't know, 70 time constants to complete. The magenta curve takes about, I don't know, maybe 40, and the black curve, which is, I don't know, which is how many tanks, which is r equal to 0.7, takes about 20 time constants to complete. And that's because you make a change in Qin. Okay, by the way, this is Qin. So Q out will be Qin at final steady state, and the recycled flow will be, so this guy will be 1 over 1 minus r times Qin. So when r is large, so you see Q4 is going from 0 to 10 when r is 0.9. 10 is 1 divided by 1 minus 0.9. It's going from 0 to 5 for the magenta curve, and that's essentially 1 divided by 1 minus 0.8, 0.2. So 1 by 0.2 is 5, and similarly 1 by 0.3 is, I don't know, 3.33. Yeah, so that's, so this is 10, this is 5, this is 3.33. And similarly the offsets is also in a similar manner, because the flow change, because the flow change is larger, so the offsets are also larger than P control. But the point is, the larger the R, the more the change in the recycle flow or flow in the recycle loop, the more the change in the flow in the recycle loop, the longer it takes. And so you've got for r equal to 0.9 70 time constants being taken, for r equal to 0.8 40 time constants, for r equal to 0.7 20 time constants. Okay, if you look at CS2 on the other hand, there's only one. Let's look at the top figure. There's only one. There's a red curve and the red dotted curve. You see, in this case it doesn't really matter what R is, because all you're doing is, and you've got whatever tanks in series, and there's some recycle that's coming, and there's stuff that's going out. You're only changing this, and because you're only changing this, it behaves like tanks in series. Recycle flow changes, I mean the transient is independent of R, and that's exactly what you get, whether R is 0.9, 0.8 or 0.7. All the responses settle in about 5 time constants, whether R, it's about 5 time constants for the response to settle, whether it is R is 0.9, 0.8 or 0.7. The only thing is that if the change in R is, if R is 0.9, then what happens is you're giving a unit change. You make a change here of 1. If you make a change here of 1, then the change here is going to be, for example, R times 1. So for 0.9 is going to be 0.9. So final value of the recycle stream is going to be 0.9. And if this is 0.9, to keep this chap at 1, the fresh flow must settle at 0.1. On the other hand, if to keep this guy at 1, if R is 0.2, the fresh flow must settle at 0.2. If R is 0.7, the fresh flow must settle at 0.3. So that's what you see here. For R is equal to 0.9, the blue curve settles at 0.1. This is the flow in the fresh feed flow. The magenta curve, which is for R equal to 0.8, settles at 0.2, and the black curve, which is for R equal to 0.7, settles at 0.3. So when you add this and the recycle, what you get is a perfect step in Q naught. Yeah, perfect step. Okay, so the point here again is that in order to keep this flow fixed, this is recycle and this is fresh. In order to keep this flow fixed, recycle changes because of dynamics. In order to keep this flow fixed, this is perfectly kept fixed. In order to keep this fixed, this varies, and this is the variation in the fresh feed. But the variation is smooth, no bumps. You go from where you start to where you end. And so with P control, the conclusion is, when you're using CS1, the response is smooth. However, the response slows down significantly as R is increased. If you use CS2, overall response is smooth, it is fast, and there is no dependence on the speed of response on R, and that can be verified. All the responses here, whether it is R equal to 0.9, 0.8 or 0.7, take about 5 time constants to complete. They complete in about 5 time constants. You see, completion is in about 5 time constants. So that should count for something, yeah. Okay, so that's that. Now that we are done till here, let's continue. Let's look at PI control. If you look at PI control, CS1, you can see that when R is 0.9, response settles at 10, Q4 response settles at 10. That's the first subplot in the first figure. The blue curve, however, it is quite oscillatory. It takes forever to settle. Reduce the R, same tuning of all the level controllers, F equal to 2, A equal to 2, and the magenta curve also settles in about 2 or 3 oscillations. Reduce the R further to 0.7 and the black curve settles much earlier. However, you notice that this scale is 0. Oh, sorry. You notice that this scale is 0 to 140 time constant. This scale is 0 to 10. So there is an order of magnitude difference in the time scales. When you use CS2, response is smooth, settles in about, I don't know, 7 or 8 time constants. Yeah, I would say about 8 time constants. P controller setting is settling in about 4 or 5 time constants. This is settling in about 8 to 10 time constants. Response, there is a bump there. You got to settle at 1, but then there is a bump here. You got to settle, so there's also a bump in the volume. But the point is, response settles on the other hand, and it is much faster. On the other hand, if you're using a CS1 control structure, response takes forever to settle, can be oscillatory, quite oscillatory, and the oscillations can take forever to settle down. So that's sort of the conclusion. As recycle fraction R is increased, the response becomes more oscillatory and takes forever to settle. There's a large overshoot, and there are also undershoots due to integral action in CS1. In CS2, even with PI control, the response is much smoother, much faster, noticeably faster, 7 or 8 time constants. But there are bumps due to I action, and that's bound to be there. Okay, so this again also suggests that CS2 is much better than CS1 dynamically. It's much faster, 10 times faster. Now suppose you want to do a throughput change, the processing rate. So in CS1, what you do is you want to change the feed processing rate from X to Y. So all you do is change the set point of the Q in controller from X to Y, and you will be processing, instead of X, Y kilomoles an hour of fresh feed. In CS2 on the other hand, this is a dependent variable. If you want this flow to change by 1, but this is not independently set. What is independently set is this guy, and if this is to be changed by 1, then these are all the tanks in series, then this will also change by 1, and this will change by 1 over 1 minus R, and so the change here must also be 1 over 1 minus R. So for example, if R is 0.9 and you want to bring about a change of 1% in the fresh feed rate, then the Q naught, which is the throughput manipulator in CS2, must be changed by 1% divided by 1 minus 0.9, so actually 10%. So that's what we have here. The red curve is for CS1 and the blue curve is for CS2. You see, in CS1, the red curve, you give a simple step of 1%. This is that simple step of 1%. You give a simple step of 1% and let the response pan out. And when you're using a PI controller, the response is quite oscillatory and takes forever to settle, 100 time constant, and it's still not settled. On the other hand, if you use P control, you give the same step. The response eventually reaches at 10, but it takes forever. It takes about, 80 time constants. Yeah, so it takes about 80 time constants to settle. On the other hand, if you look at CS2, so what we do here is a step of 10% is given in Q naught. If you look at Q naught would be like this. This is Q naught. It goes from 0 to 10% in one shot. As it goes from 0 to 10%, in order to make it go to 10%, fresh feed goes to 10%. Oh, come on, man. Fresh feed goes to 10%, and then as recycle flow starts increasing, because as Q4 increases, recycle is R times Q4, so recycle would be 0.9 times of this flow. As recycle flow starts to increase, the amount of fresh flow that you need to bring in decreases, so it decreases, and you get the kind of response that you get for a PI controller. As the fresh feed increases, as Q4 increases, the response decreases. FQ in has to decrease in order to maintain Q naught at 10%. Okay, and so you get the usual bump with PI control, and in P control this bump is missing. There is no bump, there is a smooth transition. It's actually a pretty fast, the response completes in what, I don't know, maybe 8 time constants, 5-6 time constants, which is 10 times faster than P control, CS1, okay. So CS2 is significantly faster, and that's the limited point that I have been trying to make here, that when we are using CS2 it gives a significantly faster response. P control gives smooth bumpless transients with level offset. PI control, however, gives bumpy transients with no level offset. So P control for smooth process operation, P control is what is recommended. Finally, what I did was have all the tanks under level control, critically damped level controller, A equal to 2, F equal to 2, and this is the response using CS1. What I say should not be done. When the number of tanks is 8, you get the blue curve. When the number of tanks is increased to 12, you get an unstable response. So seemingly reasonable tuning of integral time being twice of the residence time and Kc being 2. For this seemingly reasonable tuning, you can see that when there are 8 tanks, the response, it has not settled in 200 time constants. It is still oscillating. So I don't know, it will settle in maybe 500 time constants. Response will never settle. With n equal to 12, you actually blow up. You get instability for the same tuning. On the other hand, if you were using C2, whether the number of tanks is 8, 12, 20, 40, it doesn't really matter. As long as each of the individual level controllers is stable, the overall response is going to be stable. Yeah. So the point is, with CS1, even as individual PI controllers are stable, the overall system goes unstable because of recycle for large N. There is no such instability if we use P only control. I'm not shown the result, but it can be proven. Okay. And so if for some reason you are forced to use CS1, don't use PI controller ever, use P control. It will smoothen out transients and it will not go unstable. So P control is recommended for both CS1 and CS2. However, with P control you get offsets in level, and if you get large offsets and start approaching high and low alarm level limits, in that case you do need overrides so that these alarm limits are not breached, and large drifts in level are brought back. But that can be done using simple overrides, which we have not covered now, but we have covered elsewhere. Okay, so that's the overall recommendation. So in summary, what I would like to say is that liquid level control for tanks in series with no recycle, P control will give smooth bumpless transients, but you'll get level offset. PI control of level will give bumpy transients with no level offset. The downstream units will see larger flow variability, and these bumps become larger as the number of tanks increases. Liquid level control for tanks in series with recycle, we see that if you are fixing the fresh feed, then because of the recycle, the overall response is significantly slower when the fresh feed is flow controlled. On the other hand, you get a much faster, order of magnitude faster dynamic response when the total fresh plus recycle is flow controlled and the fresh feed is brought in as a makeup stream. It is not fixed. So you hold a recycle flow. That seems to make sense. CS1 can go unstable for PI control with large N, even though each of the individual level controllers seem to be reasonably tuned. CS2 is always stable as long as the individual controllers are stable, whether P or PI. If you want stability in CS1, do not use I action, use only P control. CS2 will be stable for P and PI, however PI will give bumps, so overall you should be using P control for smoothing out or filtering out variability in flow. So liquid level should be P controlled. Fixing a fresh feed should be avoided because it slows down the overall plant-wide response, and for PI controllers there is also the possibility of instability. So the idea is that one should fix the total flow and bring in the fresh feed as a makeup stream for fast overall plant-wide dynamics. And this goes back to transformation of variability perspective that I keep talking about. You know, this is what we have: fresh feed, recycle, fresh feed. If I hold this, things take forever to build up or deplete, as the case may be. On the other hand, same system, if I fix this, then essentially this is fixed, and the flow controller that you use to fix it transforms variability in the recycle flow to out here so that this flow remains fixed. So the idea that we should structure our plant-wide control system in a manner that transforms variability out of the recycle loop, which we have discussed earlier. Even our dynamic results for the very simple tanks in series process seem to suggest that there is a significant dynamic advantage to it. You avoid instability, your dynamic response may be 10 times faster. And so even from the dynamic point of view, I would say that one must structure the inventory control system to transform variability out of the recycle loop. This has been a long lecture. I hope it was useful. It took me time to do this because it took time to figure everything out and put all my thoughts together and make a cohesive story out of it. I hope the story was cohesive enough. And that will be that. I will say goodbye. We'll meet again. Now I think I have much of the material for the remaining lectures ready, so I will be uploading lectures more frequently from now on, and sorry for the long break. I was trying to prepare this material. I've also derived some things which I have not presented here. Maybe we can do them as exercises. So one exercise would be, we showed that when you got a recycle system, if you have a PI controller, you can get instability. Can you derive the condition of that instability for n tanks in series? What is that condition of instability? Try and derive it. I've done it. You do it as an exercise. Alright, that's that. Thank you so much. Goodbye.